Last time we talked about trigonometric ratios and we reviewed what the trig ratios are. We looked at the three new trig ratios that are reciprocals of the ones that you already knew. And we also talked about 30, 60, 90 triangles, 45, 45, 90 triangles, and came up with the trig ratios for all of those special angles. Today we are going to be talking more about trigonometric applications. So we're going to talk about how we can actually use trig ratios to solve for measurements, whether those measurements are distances or whether those measurements are angle measures. So before we get into solving right triangles, there are two theorems that I'm going to remind you of. So the first is the Triangle Sum Theorem, which is that the sum of the measures of the angles in a triangle is 180 degrees. The second theorem that I'm going to remind you of is the Pythagorean Theorem, which tells us that in a right triangle, if you have legs A and B and hypotenuse C, then A squared plus B squared is equal to C squared. Okay, so we'll keep those in mind as we get into solving right triangles and seeing when we're able to use these theorems to help us out in trying to figure out measures within a triangle. Let's start off with a simple example. So here you are told that you have a right triangle. You are told that one of the angle measures is 65 degrees. It looks like the hypotenuse is 8, and it looks like the adjacent side is x. So here it's asking you to find what the measure of side x is in this triangle. So let's go ahead and label what we have here. So in relation to the 65-degree angle, we know 8 is the hypotenuse and x is the adjacent side. Now we want to write a trig ratio that involves all this information, including x, so that we can solve for x. So since we have the adjacent side we're trying to find, and we are given the hypotenuse, it looks like we should probably use cosine. So cosine of 65 degrees is equal to the adjacent over the hypotenuse, which is x over 8. So now we have an equation that we can use to solve for x. So to get x by itself, we multiply both sides by 8. So we have x is equal to 8 times cosine of 65. Make sure in your calculator you are in degree mode before you plug this in. And then you can go ahead and just plug in 8 times cosine of 65 degrees, and that comes out to be about 3.38 or so. Okay, so that's how you would find a missing side in a right triangle. Now let's talk about, or let's actually do an example where we find the measure of an angle in a right triangle. So here's example 2. You're given 3 of the sides, and you are trying to find the measure of angle theta, which is the one in the bottom right there. Let's go ahead and label all the sides in relation to angle theta. So we have the hypotenuse, which is across from the right angle, and then across from theta is 3, so that's opposite, and adjacent, or next to it, the one that's not the hypotenuse, is the adjacent side, 4. Okay, so actually with a problem like this, because you have the measures of all 3 sides, you can actually use any of the trig ratios that you know, right? Because we just need to involve the angle theta, so it'll be sine of theta equals 3 over 5, or you could do cosine of theta is equal to 4 over 5, or you could do tangent of theta is equal to 3 over 4. In any of those cases, if you were to solve it, you will end up with the same measurement for theta. So let's go ahead and try using our sine ratio here. So if we're using the sine ratio, we want to use the opposite side and the hypotenuse, so that's 3 over 5. So 3 over 5 is 0.6. Now to find the measure of an angle, this is where using the inverse sine function on your calculator is going to come in handy. So because you are trying to solve for theta, we have to take the inverse sine in order to get theta by itself. So make sure your calculator is in degree mode, otherwise it will give you an answer but in radians. So if you put it in degree mode, then your answer will be in degrees. So you want to plug in sine inverse of 0.6, or if you wanted to, you could do sine inverse of 3 over 5 and then end parentheses. That's fine too. And that should come out to be about 36.87 or so. Now if you did the same thing with cosine, but you would use 4 over 5, so cosine theta equals 4 over 5, and you did cosine inverse of 0.8, you should end up with the exact same answer. And same with tangent. Okay, let's get into what we call solving right triangles. So we've looked at two examples, one where you're trying to find the measure of a side, one where you're trying to find the measure of an angle. Now when you're asked to solve a right triangle, that means you are finding the measure of all the sides and angles. So there are two cases that you are going to run into when you're asked to solve a right triangle. In the first case, you are going to have an acute angle and you are going to have a side. Now remember, because these are right triangles, you actually already know that one of the angles is going to be a right angle, is a 90-degree angle. So in this case, if you have a 90-degree angle, you have the measure of one of the acute angles, the first thing you can do is to find that third angle using the Triangle Sum Theorem, right? The fact that all three angles will add to 180. Second, now you have one of the sides and you still need to find the other two sides. So to find another side, you will have to write a trig equation that includes an unknown side as the variable. It doesn't matter which side you pick first, as long as you use the correct trig ratio that goes along with that side. Okay, so then once you've done that, now you have two of the sides, you still have one side left to find, and in order to find that last side, you actually have two options. You can either write another trig equation, or you can use the Pythagorean theorem to find that third side. Okay, so that's the first case. In the second case, you are given two sides. So that means you're still missing one of the sides and two of the angles. Remember, that third angle we already know is a right angle. So first, we can find the third side using the Pythagorean theorem. Okay, so now we have all three sides. So now we still need to find the other two angles. So next, you'll write a trig equation that includes an unknown angle, and then you'll have to do inverse trig of whatever that ratio is. And then, for the last step, you can either write another trig equation to get that last angle, or you can use the Triangle Sum Theorem, the fact that all three angles have to add to 180, to find the last angle. Okay, let's go ahead and take a look at an example. We'll do an example of both cases. So here in example 3, let's see which case we have here. So it looks like we have one side and one acute angle. So this looks like case 1. Okay, so in case 1, first thing you want to do is find the measure of that third angle. So in this case, we have a 90-degree angle, we have a 75-degree angle. So just subtract both of those from 180, and that will give us the last angle. So that's 15 degrees. Okay, so now we still have two sides we need to solve for, A and B. So let's say we wanted to solve for A first. So now we need to write a trig ratio involving that side, involving A, that will allow us to solve for A. Now it's up to you if you want to use the 75-degree angle or if you want to use the 15-degree angle, as long as you make sure that A is either the opposite, if it's across from the 75-degree angle, or adjacent, because it's next to the 15-degree angle. I'm going to say that we're going to use the 75-degree angle, and I would suggest using that just in case you messed up in the first step, right? You don't want to have subtracted incorrectly in the first step and be using the wrong angle measurement to get that final answer for A. So to be on the safe side, use information that was given to you in the problem. So let's say we use the 75-degree angle. We're trying to find A. We also have the hypotenuse, which is 17. So it looks like we have the opposite side, which we're solving for, and the hypotenuse. So it looks like we should use the sine ratio. So sine of 75 is equal to A over 17. We'll get A by itself, multiply both sides by 17, and that comes out to be about 16.42. Okay, now for the last step, you have multiple options. You can either use the information that you already have and write another trig ratio, or you can use the new information that you've gotten from solving for A. You have the hypotenuse, and you can use the Pythagorean theorem to get B. Just for practice, we're going to go ahead and use another trig ratio to solve for B. Again, I'm going to stick with using the 75-degree angle. So B in this case is the adjacent side, and we'll use 17 just because that was given to us. That's the hypotenuse. So that means cosine of 75 is equal to B over 17. And we'll get B by itself, so this is 17 times cosine of 75, and that comes out to be about 4.4. And now we've successfully solved for all the missing parts in this problem, right? We were missing three things. We were missing an angle, we were missing two sides, and we've successfully solved for that. Okay, let's look at another example. So in this case, you're clearly given two sides, and you don't have any of the angles. Now, in the bottom left corner there, that angle is labeled with the Greek letter beta, B-E-T-A, beta, right? And the top one is theta, T-H-E-T-A. And we need to solve for both of those angles, and we also need to solve for the missing side, which is labeled A. So in this case, in case number 2, when you're given two sides, first, you can solve for the third side by using the Pythagorean theorem. So we have a squared plus 6 squared equals 12 squared. Get a squared by itself. So we have a is equal to the square root of 108, which simplifies to 6 root 3. Okay, now we need to solve for the two angle measures. Now it's up to you which angle measure you want to solve for first. I'll go ahead and solve for beta. So we are trying to solve for beta. Use information that was given to you already, so the 6 and the 12. 6 is adjacent to beta, and 12 is the hypotenuse. So it looks like we should use cosine. Cosine beta is equal to 6 over 12, which is 1/2. And then using inverse cosine of 1/2 should give you 60 degrees. Okay, and then for the last angle measure, we can now use the Triangle Sum Theorem and say, well, if I've solved for the second angle measure, and I know that the other angle measure is a right angle, then we can just subtract all of that from 180 to get the last angle measure. So that's 180 minus 60 minus 90, which is equal to 30. Let's do another example, this time more of a word problem. A straight road leads from an ocean beach at a constant upward angle of 3 degrees. How high above sea level is the road at the point 1 mile from the beach? Okay, so here's a picture. We have the ocean here on the left, and the road that leads from an ocean, so it's going away from the ocean, goes up at an upward angle of 3 degrees. So obviously here it's been exaggerated so we can actually draw it. And 1 mile away from the beach would be 5,280 feet. Now you could absolutely use 1 mile. You would just use 1. The only thing is that the height above sea level will be some fractional part of a mile, which is a little bit harder to understand. And normally when we talk about how high above sea level, particularly something that's this close, just a mile away, we would probably want to use feet. Okay, so if we're trying to solve for the height above sea level, which is the measurement across from the 3-degree angle, and it looks like 5,280 feet is across from the 90-degree angle, that must mean that's the hypotenuse. So we want to use our sine ratio here. So sine of 3 degrees is equal to h over 5280. We'll get h by itself by multiplying both sides by 5,280. And this comes out to be about 276.33 feet. So at 1 mile away from the ocean, the road is about 276 feet above sea level. Now, if you did use 1 mile instead of 5,280 feet, you would have gotten something like 0.05 miles above sea level, which is a little bit harder to imagine than 276 feet, but is absolutely a correct answer. Okay, our last example is an example of what we call indirect measurement. So here, a flagpole casts a 60-foot shadow when the angle of elevation of the sun is 35 degrees. Find the height of the flagpole. So here's an example where you would be able to come up with a measurement of the flagpole without needing to take some sort of measurement all the way up to the top of the flagpole and then bring it all the way down to the bottom just to see how tall it is. Rather, you can measure the length of the shadow, right? That's something that is measurable, and use that angle, so the tip of the shadow to the top of the flagpole, find that angle, which is also doable, and from that you can actually get the height of the flagpole. So take a look at the information you have. So across from the 35-degree angle is h, and adjacent to it is the 60-foot shadow. So it looks like here that we want to use our tangent ratio. So tangent of 35 degrees is equal to h over 60. Now we get h by itself, multiply both sides by 60, and this comes out to be about 42 feet. So the flagpole is about 42 feet high.